Hey, you guys, welcome to another exciting week. Today, we're going to be focusing on a new chapter, which is 9.1 Exponential Function. Now, this chapter will consist of a lot of information, so please pay attention very closely. And as well, you're going to be needing your calculator in some cases. Okay, for today's vocabulary word is asymptote, exponential function, and number sense as well. All right, so let's see what's today's lesson is all about. So an exponential function is a function of the form as y equals a times your b to the power of x. So exponential function, it means that your variable is gonna be to the power x, where a is not equal to 0, your b has to be greater than 0, and your b cannot equal to 1 as well. And the exponent must be as a variable. It's always going to be as a variable when we're dealing with exponential functions. All right. So here we have a sample table, and it's saying, does the table represent a linear or exponential function? And we need to explain why. So let's notice this. We notice that our table is going by 0, 1, 2, 3, -1, -3, -9, -27. All right, so let's go ahead and analyze this. Since the x values are increasing by ones, it's increasing by ones, and the y values are basically, we see a pattern that is being a multiples of 3. So times 3, times 3, times 3. It means that -1 times 3 will get -3. -3 times 3, we get -9. -9 times 3, we get -27. If you get this format, you get a constant number on the top, which is your x values, and a constant number that is being a multiple on the y values, then this is going to be considered a exponential function. Make sure that on the y values, it's going to be a multiple of numbers. And on top, it could be added. All right, so let me go ahead and provide you the information to this. All right. So as you can see, the difference between the x values is going to be a 1. The ratio between the y values are going by 3s. So the table represents an exponential function. There's a common difference between consecutive x values and a common ratio between the corresponding y values. You could also try putting this information into the calculator, and you could tell that it's an exponential function, and we're gonna give you more information later on in the slides, okay? All right, does this rule represent a linear or exponential function? We have y equals 3x. Notice our formula here in the corner. If we're dealing with exponential function, it means our variable has to be as an exponent. This x variable is not as an exponent. So therefore, this is not a exponential function. This is more as a linear function. So the rule represents a linear function because it is in the form as y equals mx plus b. The independent variable x is not as an exponent, like I mentioned. So it's just a couple of examples so you could determine which one looks like an exponent or not, if it's a linear or not. All right, let's try one more time. All right, we have a multiple choice. Does this represent an exponential function? Okay, let's go back to this question number 1. The top part for your x values has to be increasing by 1, and well, it could be increasing by whatever number as long as it's constant by the same number. And on the bottom has to be a multiple. by any number. All right, let's look at this one. So far, from here to here, it's increasing by 1. So it's plus 1, plus 1, plus 1. So far, so good. But from here to here, it's being multiplied by -1. And from here to here is multiplied by 3. From here to here, it's added by 2. So therefore, we don't see a pattern that is being a multiplication. Here it could be a multiple by 3, or it could be added by 2 as well. So let's say if we add this by 2, added by 2, added by 2, still it's not a multiplication. So therefore we can eliminate the yeses, and we have this. Let's say letter A. No, the X value does not increase by a constant amount. The X value, it is increasing by a constant amount. Let's look at B. B, the Y value are not multiplied by a constant number. This is your correct answer because it's not being multiplied. Every time it's going to be an exponential function, it has to be multiplied. Okay? So just keep that in mind. All right, so here we have a couple of details of how it looks as a graph. So whenever you have a graph that it looks like it's increasing, you have an exponential growth. The horizontal asymptote is basically this curve of the line, the exponential function. It means that this is never going to be crossing the horizontal line at y equals 0. It means that this is going to continue. It's going to get really, really close to the y equal to 0, but intentionally it's going to go to all the way to -infinity values. It's never going to be touching the exact value as y equals 0. Okay. Your range, it's from 0 all the way to -infinity. It could be also be written as y greater than 0. Notice I'm not putting it as equal. If we put it as equal, then it's gonna eliminate that horizontal isotope. And that's not what we want, because that's not gonna make this exponential growth as a true statement. Our domain is going from -infinity to infinity. It means that your X values are all real numbers. This is the symbol for all real numbers. So just keep in mind, your range, it's y greater than 0 because of the isotope 0. Over here we have another graph, but it looks like it's been decreasing. This is called a decay, exponential decay. The other one was called a growth. This is a decay. Again, our horizontal isotope is at y equals 0 because this is going to continue all the way to positive infinity values on the X values, but it's never going to cross the y equals 0. Your domain is always going to be all real numbers. All real numbers. So that is just something for you to keep in mind. All right, another thing that you need to keep in mind is that an exponential function is a function of the form as y equals a times b to the power x, where your a is not equal 0, b is greater than 0, b is not equal 1, and x is a real number. So these two are just different types of graphs. Let's suppose you have your base is a 2 to the power of x, then you have a growth. When you have a negative, then it's just being reflected across the x-axis. But notice, when you have a decimal place, when you have a decimal place or like a fraction to the power of x, then you're gonna have a decay. And when you have a negative, then it's gonna be reflected across the x-axis, okay? So just keep that in mind, different forms of how to look at to the graph. Let's talk about asymptotes. So the x-axis is a horizontal isotope at a y equals 0 for an exponential function of the form as y equals ax a times b to the power of x. The values, the y values approaches 0, but never actually reach 0. Like I mentioned, it's gonna go all the way to infinity. Let's suppose for the blue one, all the way to the negative infinity values, but it's never gonna be crossing the asymptote. Same thing as over here. You have all the way to positive infinity values, but it's never gonna cross the y equals 0. Do not crosses the x-axis in this case. So let's suppose we have a couple examples. Let's say you have a curve going like this. You know, let's suppose. All right. Well, in matter of fact, let's do it a little bit more precise. You have something like this, going like that. Your horizontal isotope is going to be basically the value underneath this. So this dotted line, that is going to be your horizontal isotope at a y equals 2. It means that this purple line that is going to the negative infinity values is never going to cross the isotope line at the value of 2. It's just going to go all the way to infinity, but it's never going to cross 2. As far for your range is going to be, sorry, it's because this thing is a little bit glitchy. Your range is going to be y greater than 2, greater than the isotope, because the y values have to be greater than the isotope, because this line is never going to be touching at that y value. As far for your domain, it's going from negative infinity to infinity, so it's going to be all real numbers. If we have another example, let's say you have a curve going from here, let's say right, you have a curve like that. Then your isotope in this case is gonna be at right here at the -2. Y equals -2. Your range is gonna be y less than -2, because now you have your y values on the lower side. Your domain is gonna be the same thing, or real numbers, because you have positive infinity values and negative infinity values for the domain. So just keep that in mind, but mostly in order for you to see this, like this type of examples at a different horizontal isotopes, you probably gonna have an equation having like a times b to the power of x, and then let's say for the first one, since your isotope is at 2, then you could have like a +2. This +2 is your horizontal asymptote. Your horizontal asymptote. But in this lesson, we're just going to be focusing more on this equation. And the reason they don't show anything more is because you have an imaginary plus 0, which means your isotope is going at y equals 0, your horizontal asymptote. Okay, because you have plus 0, then it will not show it to you in the equation. Just keep that in mind for yourself. All right, let's go ahead and practice some problems. What is a graph of y equals 3 times 2 to the power x? Identify domain, range, express the using inequality. All right. Our initial value, a, in this case, if we look at the formula here on the corner, a is going to be our 3. Your base value is going to be a 2, based on this formula in the corner again. Your domain and range. Let's go ahead and use the calculator to look at this. All right, let's go ahead and use graphing. And let's go ahead and graph this. So we have 3 times 2, and then to the power of x. This is our graph. We notice that the graph here is going from negative infinity values all the way to positive infinity values on the domain area. So in this case, your domain is going to be all real numbers. As for your range, here in your range, let me go ahead and freeze this. Your range, basically, your horizontal isotope is going at this location at the dotted red line. Notice it looks like it's gonna be crossing or it's gonna be touching, but if you do a lot of zoom in and based on a lot of research, it's never gonna be crossing this line, never. So this line is crossing the y-axis at y equals 0. So that's gonna be your horizontal line. And as well, look at the expression. You don't have something here that you have a plus 0, but it's imaginary. It will not show it to you. So this is still the same thing. Y equals 0 and plus 0 here. It shows you that that's your asymptote. Again, that line is never gonna cross at that location. So in this case, since we have this as y equals 0, then the line, our graph is going upward, so it has to be bigger than 0. It cannot be equal again. So the range is y greater than 0. It's not equal. All right, our x-intercepts. Our x-intercept basically, hold on. Having a little bit of technical issues. So if we look at the graph here, is this graph gonna intersect somewhere in the x-axis? No. So we don't have anything for the x-intercept. But as far for the y-intercept, if we look at the formula here, our a is always gonna be our y-intercept, which is 3. Okay? Again, I'm having a little bit of technical issues. Okay. Your horizontal isotope, we already know it's y equals 0. Is it decreasing or increasing? All right, this line is going upwards, so it's gonna be increasing. So in this case, we're gonna select increasing. All right, for x-intercept, it's none. All right, let's go ahead and practice another one. Graph the function of 2 to the power x. Remember our formula? We have a times b to the power of x. In this case, we don't have an a, so it's an imaginary 1. Our b is going to be a 2. Our domain and range. All right. Domain, let's look at this on the calculator. Let's go ahead and press tab up and let's edit this. Our equation is just 2 to the power x, enter. All right, kind of seems like the same one from the previous example. So we know that our domain is going from negative infinity, x values, all the way to positive infinity. So therefore your domain here is gonna be all real numbers. This thing is not writing properly. I don't know why. All real numbers. All right, your range. Notice again, your isotope is going at a y equals 0, your horizontal isotope. As a matter of fact, let me go ahead and grab this image. Let me grab this image and paste it over here. For this part. Santeleta, it's gonna seem Santeleta. All right. So our horizontal isotope is like right here in the red dotted line at a y equals 0. So we already have that horizontal isotope is y equals 0. Then from here, this area, we're looking for our range. Since this graph is going upwards, it means that your range has to be y greater than 0. So y greater than 0, that's your range. X-intercepts, again, this line is never gonna intercept, so this is none. Your y-intercept is gonna be, again, based on the formula here, your A is gonna be your y-intercept. So in this case, it's at 1 because we have an imaginary 1 for your A. Is this increasing or decreasing? Well, the graph looks like it's been increasing, going to this direction. So it's increasing. To fill out these gaps from the table, you could just, from this graph, you could just click Control T for your table and go to the value where it says -3, and then just fill in these values. So -3, we have 0.125. So 0.125. For the 0, we have a 1. We have a 0.5 here. 0.25. And for the 1, we have a 2. And here we have a 4, and then we have a, let me just scroll this a little bit down. And then we have an 8. What happened, basically, you just implement this value, substitute it with the X, and you're gonna get a result. Okay? So that's basically what you're doing. All right. What is the graph of the function of y equals 0.5 times 3 to the power x? Identify domain and range of the function. Express the range using an inequality. We notice that our a is, it's a fraction, okay? Times 3 to the power x. All right, let's go ahead and exit here, Control T, tab up, and let's edit this information. We have 0.5 times 3 to the power x. Okay, it seems to me that it's been increasing. So we could start eliminating the options where this decreasing. And let's look at the range. Can the range be equal to the isotope at 0? No. It's always gonna be not equal. So it has to be bigger and not equal. So it's letter A in this case. All right. Here we have a real world scenario. Suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. So the function is being provided to you at 30 times 2 to the power of x gives the population after x weeks. How many beetles will there be after 56 days? All right. So how many days are in a week? There's 7 days in a week. So technically we need to get 56 divided by 7 days. It's gonna provide us how many weeks there is. In this case, there are 8 weeks. So that 8, we just need to substitute it to the value of x. So we have y equals 30 times 2 to the power 8. Let's use our calculator in this case. Let's go to home and then calculate. Well, let's type it in. 30 times 2 and then to the power of 8. Enter. We get 7,680. So that's how many videos we get. So 7,680 videos we get within 56 days. So within 56 days. All right. Let's do something similar. So initial population of 20 rabbits triples every half year, sorry. The function is being provided to you. Gives the population after X half years period. How many rabbits will there be after 3 years? So if you're gonna split a year in half, you're gonna have two sections every 6 months, basically. So let's say your first half is month 1 through 6. Your second half is from 6 through 12, and that makes all of this into a year. So that means that you have 2 periods within a year, and you have 3 years. So 3 times 2 makes it 6 periods in total. 6 half periods in total within the 3 years. So that's 6 you're gonna be implementing into the equation. Got 20 times 3 to the power 6. Let's go back to the calculator. We have 20 times 3 to the power of 6. And we get 14,580. So 14,580 rabbits, which is letter D. All right. So that's basically today's lesson. We're just doing a growth and decay and substituting values in TX, knowing our domain and range, isotopes as well. If you have any further questions, please let me know. Thank you for watching. You have a great day. Bye.